Now let's look at a very important class of continuous distribution called a triangular distribution. I have an example here. A project is about to finish with one last step, but this completion of this last step depends on many factors. If all goes well, it can finish in one day, which is the most optimistic case. The most pessimistic case, however, is that it will take 10 days. The most likely, however, is that this step will take 7 days. Use Excel to simulate the distribution of the completion time of this last step. Now, this kind of business situation are everywhere. You have a best case, you have a worst case, and you have a most likely case. In statistical sense, this is captured by what we call a triangular distribution, and its probability density function is captured here. You have a worst case, which is around A, and you have a best case around B, and the most likely case, the mode, is captured by this parameter C. And A is less than C, which is less than B. And how do you simulate this distribution? Well, it turns out it's straightforward as long as we understand the cumulative distribution of this triangular distribution. Now, this is the cumulative curve. By definition, it's from 0 to 1, and it is the cumulative density is worked out in this formula. If you look at it, basically there are two parts. If the cumulative distribution is over this threshold, which is C minus A over B minus A, then it's this formula. If it is below this threshold, then it's this part. And of course, below A it's 0, and above B it's 1. So that's the complete CDF. We can do some reverse engineering, figure out if you give me the CDF, I can figure out the X. And that's the key in terms of simulation. So what we will do is we will use Excel to draw a CDF number. Again, use our familiar rand function, and then we'll, based on this number, work out the exact X, and that's how we will draw from this distribution. Now, look at this model here. This min and max and most likely case, the three parameters are being defined here. To make my formula a bit more simple, I actually use range names. So I call A, PA, B, C, PC, and B, PB. Okay, and as you can see, I set up the rounds, and first of all, I'll let it run 1,000 round, and in column B is basically drawing a random number from 0 to 1, and that's straightforward. And secondly, there's an intermediate step to tell us which segments does this CDF fall into. It is over or below. If it is over, then this is step. If it is 0, then this is the reverse engineering part, the square root of this. I'll be able to know exactly what X value is. Okay, and if it is over the threshold, it's this number. So it is how we draw the outcome, starting with the CDF. Now, if I draw 1,000 times, and you can see the many, I took the average of those draw. It turns out to be 5.6, and from the formula, we also know the average should be around 6. Now, I also plotted a histogram based on this 1,000 draw. You can see it is kind of triangular shape, and due to the inherent noise here, it is not very smooth. So what I did next is let it run 50,000 times, so many more rounds, and you can see it's gonna be a very long table here. Now, I used a histogram to to look at the distribution of that. And as we expect, as you draw more and more from this random distribution, it becomes smoother and smoother. And this indeed tells us we are drawing from the right distribution. Now, for the 50,000 run, if you take the average, here, you can see that it's 5.939. So it is getting pretty close to the true value of average here. So with this tool, we can use in many business situations where there is a worst case, best case, and most likely case.